Hello, just like in the previous video, this video is going to focus on a specific pattern, in this case, what we call difference of two squares. If you come from a different school, you might be used to it being called DOTS, which is difference of perfect squares, but I prefer difference of two squares because it focuses on what it looks like in the end. So what does it look like from the unexpanded perspective? We've got a minus b times a plus b. Or it might be the other way around, a plus b times a minus b. It doesn't matter. Because multiplication has a commutative law, which means that it doesn't matter which way you multiply two things together, 3 times 7 equals 7 times 3, then it could be in either format, but that's, again, what you're looking for. One term minus a second term multiplied by one term plus a second term, or vice versa. Okay, and it just needs to fit that pattern. And again, you can see we've got 3 examples here, which has a look at this. It fits the difference of two squares pattern exactly, although it may look unfamiliar. And as I said in the previous video, which I promise I will try not to harp on about it too much, your fundamental skill that you need to develop is looking at a problem, and instead of going straight for, I'll do the chicken beak method or the box method to expand it, going, oh, I see it fits a pattern. I see it's a difference of two squares. I'm therefore going to jump straight to the answer, if you like, or the expansion without having to do the intermediary steps. So your efficiency is increased, but you do need to practice that mathy sense of seeing a pattern. So what does it look like? A minus b times a plus b. In both instances, it simply is a squared minus b squared. Okay, it doesn't matter which, whether it's minus plus or plus minus, it'll always end up as a squared minus b squared. That is the pattern. And we can see now why it's called difference of two squares. Whenever you hear the word difference in mathematics, it almost always implies a subtraction operation or the result from subtraction. Difference of two, there's two of them, never a middle term, and squares because we've got the first term squared minus the second term squared. It is easy and difficult as that. Alrighty, let's put it into practice. X minus 3 times x plus 3. We can see that it fits the pattern. Our thinking is that A is 3. Oops, incorrect. A is x and B is 3. We just keep that in our heads, and of course with practice we're not even consciously thinking that. We can just see the pattern. So we square the first one, x squared. It's always a difference, so minus, and then we square the second one, which we can do in our head. 3 squared is 9. Okay, I'll put that as a little arrow here, just in case you're just reading the notes back and you can see 3 squared is equal to 9. That is basically it. All we can do now is make it more difficult, like example 2. 2x plus a half times 2x minus a half. Again, the thinking. A is 2x, B is equal to a half. Okay, try to avoid turning into 0.5. I think you'll do better if you leave it as a half when you can. Pause the video, have a go at it. You can see I've done it in 2 lines. See if you can do it in 2 lines without using the chicken beak method, without using the box method. Okay, hopefully you've paused the video and worked that out, but if you haven't, no worries. This middle line is optional. If you can just go straight to the final line, even better, but I don't expect you to. Square the first term. So the first term is 2x. I put the 2x in brackets to remind myself that because I have to, because I'm squaring the entirety of 2x. If I just went 2x squared, that would mean 2 multiplied by x squared. BDMAS tells us that, right? Brackets, then indices, so the 2 belongs to the x, and then multiplication, 2 times x squared. So we can't write it as 2x squared. We have to put the brackets in to know that we're squaring the entirety of that term, and then minus, and then a half squared. Again, I put brackets to make it unambiguous. I know what I'm squaring, the whole lot. Okay, and then I'm just going to simplify that. So 2x squared, I'm going to go 2x times 2x, so 2 2s are 4, and x times x is x squared, and a half times a half. Hopefully you know that a half of a half is a quarter. If you don't, then multiply tops, multiply bottoms. 1 times 1 is 1, and 2 times 2 is 4. Square the top, square the bottom. And that's basically it for example 2. Example 3. We've got scary square roots in there, but it doesn't make a difference. It's exactly the same concept. So what are our terms? where we've got a is equal to x squared and we've got b is equal to the square root of x. Okay, they are our two terms, and we simply apply dots to that. Pause the video, have a go yourself. Hopefully you did that pause, and if you didn't, it's up to you. There's a bit going on here, so I'd definitely use a second line, I think, which is square the first term minus square the second term, like so. Okay, just straightforward like that. And then I'm going to sort of simplify each of the expressions in brackets here. So x squared squared is x to the power of 4. And then the second one is root x squared. Remember that the square root and the square symbol basically cancel each other out. So root x times root x is just x. And so we've got x to the power of 4 minus x. And that is fully expanded now. That's basically it. Now, I've got a third example here. Oh, a fourth example, beg your pardon. 3x minus 9 times x plus 3. It absolutely does not fit the pattern of a dots expression, because this and this is different from this and this. So it doesn't fit the pattern, right? But it almost feels like it nearly does. Maybe? Because if you look at this first term here, you'll see that there's a common factor, a number that goes both into 3x and 9. So this is an example of a hidden difference of two squares problem. And you could be tempted to simply use box method or chicken beak method to expand that. And I wouldn't blame you, but what we want to develop over time is working more effectively, working more efficiently. And sometimes that means digging beyond the surface problem to uncover a pattern that we can use, knowing that where possible, setting using a rule is going to be more effective than doing it longhand. Okay, less likely to be a calculation error because you've got fewer calculations you're doing, and a time saver as well. In this instance, looking at that first term, I can see there's a common factor of 3, so I'm going to factorize the 3 out. We are going to cover factorizing in the second part of this algebra unit, but this should be stuff that you're used to from grade 8, I would hope, taking it, or maybe even grade 7, taking it a common factor of 3. So I'll do that in one fell swoop. 3, and what am I left with? Well, 3 times x is 3x, and 3 times 3 is 9. And I'm hoping you can now see that there is a really simple difference of two squares problem left here, x minus 3 times x plus 3. And so away I go. 3 multiplied by, I've got to keep the brackets in here, but now I can apply dots to the last two terms there, the x minus 3 times the x plus 3. Square the x minus square the 3. So I've got 3 outside of x squared minus 9. And because this is an expansion problem, I then need to do a final expansion so there are no brackets left whatsoever. 3x squared minus 27. And that's basically it. You're done. You can stop the video now and do some problems by yourself if you like. But just as an additional bonus extra just for you, let's have a look at what it would look like from the box method perspective for this problem. I'll keep it zoomed out so you can see it. So we would have, it's not too bad, but I'm saying that it's not as easy as it could be. 3x minus 9 and x plus 3 here. So 3x times x is 3x squared, minus 9 times x is minus 9x. Minus 3x times 3x is 9x, and then minus 9 plus 3 is plus 27. So you've done that. Now you can see that the minus 9x plus the plus 9x cancels each other out, and you're left with 3x squared plus 27. What did I get wrong here? I've made a mistake. Oh, I've gone minus 9 times positive 3 is positive 27. Make that a minus there. Make that a minus there. Now I'm done. And it's the same as the answer we had on example 4. Now, I did that to show you that it's got slightly more complicated by using the box method. And I'm not a person who makes deliberate mistakes in my videos or on my board work. Not usually anyway, and I didn't make a deliberate mistake there. But it's an example of where, you've got quite a few calculations going on in your head, and it's kind of easy to make a simple error like that. Luckily, I had the problem on the left-hand side, so I knew it was wrong, and I was able to quickly recover, but you don't always have that. So this process here, being a little bit more simple, caused me to make fewer errors. So it's definitely worth doing. Okay, I'll leave the video here and have a go at doing some of the work from the textbook.